The James Webb Space Telescope has finally launched. And that's exciting, not just for astrophysicists, but for all space lovers. What makes the Webb telescope new and different? What is it looking for? And what may it discover? That's what we'll talk about today. The James Webb Space Telescope is a joint project between NASA, ESA, and the Canadian Space Agency. I've heard astrophysicists going on about it since I was a student. In 1919, the Webb telescope was scheduled for launch in 2007, but in 2003, a redesign pushed the date to 2010. In 2005, it turned out that the cost estimate didn't pan out. The whole thing was replanned and the launch date moved to 2013, and then to 2015, and then to 2018, and then some further delay made that 2020, and then COVID happened. It was finally launched on Christmas Day 2021 after more than 3 decades of planning.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Now everyone hopes the wait was worth it. The James Webb Telescope is an infrared telescope. It's equipped with 4 different instruments that can detect light in the wavelength regime from 0.6 to 28 micrometers. So that's at the long wavelength end of visible light and then below that. The previous infrared telescope was the Spitzer telescope, but it required liquid helium for cooling, and that ran out in 2009. After that, the Spitzer telescope operated with reduced functionality until it was retired in 2020. The James Webb telescope will have a better resolution than Spitzer. Here is the simulation of how much better. On the left is the Spitzer resolution, and on the right what we expect from Webb in comparison. Indeed, a group of astrophysicists have done a simulation of a far-field image from Webb into which you can zoom and zoom and zoom. Link to their paper and website is in the info below. What's so great about infrared light? Well, each wavelength range is good for something else. Infrared light in particular is good to see through dust, and space is full of dust. Dust is made of small particles, and often they are of a size that's about the same as the wavelength of visible light. This means visible light scatters a lot on dust. Infrared light is scattered far less because of the longer wavelength, so one can use it to see through dust. This is interesting, for example, because a lot of galaxies and galaxy clusters are surrounded by dust, so we don't really know what's going on inside. Here are example images from the Hubble Space Telescope, on the left in the visible range, and on the right in the infrared range. Look how the dust has basically disappeared. Now you can see inside. The James Webb Telescope can do that too, but at higher resolution. And compared to Hubble, Webb will have a larger field of view, covering more than 50 times the area that Hubble covers. Another reason why infrared is great is that as the universe expands, wavelengths stretch. So the light from early stars and galaxies becomes shifted to the red. This means the better you can measure on the red end, the more you can see of the early stars and galaxies. That Webb is an infrared telescope is also the reason why the mirror is gold. Gold is not the greatest reflector in the visible range, but it is a great reflector in the infrared. It's a tiny amount of gold that's been used for those mirrors, because the cover is only about 100 nanometers thick. In total, that's less than 50 grams of gold. That other big piece on the telescope, that's the sunshield. It's there to keep the instruments cool. Webb has 4 different instruments, each of which can detect somewhat different properties of the light that the telescope collects. By the end of January, the Webb telescope reached its final position, which is the Lagrange point 2 of the Sun-Earth system. That's farther away from the Sun than we are. The good thing about the Lagrange point is that the telescope can orbit around it with only small corrections, so it won't need a lot of fuel. The fuel supply for the propulsion system is designed to last for about 10 years, but maybe in 10 years it'll be possible to refill it. The sun shield will block emissions from both the sun and also the Earth. The temperature differences between the two sides are remarkable. On the side facing towards the sun, it's as high as 80 degrees Celsius, and on the side facing out into space, just 40 degrees above absolute zero. Still, for one of the instruments on board the Webb telescope, that isn't cold enough. It needs to be cooled to 7 degrees above absolute zero. Webb does that with a cooling system that won't just exhaust the supply of a cooling agent, but that can keep on going as long as the equipment doesn't fail and as long as it has power. Where does the power come from? It comes from the sun. Lots of solar power out there in space. So what do astrophysicists want to do with the Webb telescope? Well, the way that it works in astrophysics is that you apply for time with the telescope so you can collect the data you want. The Webb telescope will be used by those groups whose research proposals have been accepted, and the people who worked on the telescope development have some time reserved for themselves. You can look up on the website which research programs have been accepted. Here's an overview on the topics. I will leave you a link in the info below so you can look at the complete list yourself. The observation cycles will each go about a year. The first cycle will start after Webb has completed checks, probably around June this year. As you can see, the scientific program covers quite a variety of topics. One is scanning exoplanets for signs of molecules that might signal the presence of life. Infrared light is good for that because the absorption signatures of molecules like oxygen, water, carbon dioxide, ozone, and methane are in that range. Another big bunch of topics is the formation of stars and solar systems that is often obscured in other wavelength ranges. From Webb, we might learn a lot about how all that dust manages to clump together and form planets. There's also the dust itself. I know I said that you can use infrared light to see through dust, but at somewhat shorter wavelengths, you will also begin to test the chemical makeup of dust clouds. And some researchers want to use the Webb telescope to look at objects inside the solar system. For example, at asteroids, to find out whether there's water on them or something else. This would be very helpful to find out where the water on Earth comes from, which is somewhat of a mystery. And that again would be very helpful to understand how likely it is that life developed elsewhere in the universe. All of this is pretty cool, but I'm personally most excited about the observations on young galaxies and extremely high redshifts early in the universe. The youngest galaxy that the Hubble telescope has seen has been estimated to date back to about 400 million years after the Big Bang. Webb should be able to see back to about 100 million years after the Big Bang. That's very interesting because the way that galaxies form tells us something about the matter in the universe, in particular about dark matter and its role in structure formation. In the currently most widely accepted theory for cosmology, the large galaxies we see today build very gradually by merging smaller galaxies. This figure shows how astrophysicists think this works. All the symbols here are galaxies, and the larger the symbol, the larger the galaxy. Time increases from the bottom up. At the beginning, you have all these tiny galaxies, and then they join to increasingly larger ones. What you can see from this graph is that if this theory is correct, there basically shouldn't be any large galaxies at very early times. But is this correct? This figure shows the predictions from the Millenium Simulation in comparison to data. You can see two things here. One is that there isn't a lot of data at the moment, but also that it seems like the data is way off the simulation. The Millenium Simulation was a large computer simulation for structure formation in the standard model of cosmology. In such a simulation, you basically distribute dark matter in the early universe, and then you let it clump, following its own gravitational pull. Normal matter mostly follows the gravitational pull of the dark matter, but then the normal matter sticks together better and forms stars, which dark matter doesn't do, or at least it isn't expected to do it. The Millenium Simulation used about 10 billion particles to study structure formation. That was pretty amazing in 2005, but today computing power has much improved. The newest simulation for structure formation is the Uchuhu simulation that was just released a few months ago. It contains about 2 trillion particles, or to be precise, 2,097,152,000,000. You can also download this data yourself if you want, at least if you have 125 terabytes of free disk space. There will, without doubt, soon be papers coming out that quantify the structures they have found in this simulation. They will probably confirm the findings of the earlier simulations, namely that galaxy formation with dark matter takes a long time. You don't expect to see large galaxies early on in the universe if the standard model of cosmology is right. If the Webb telescope sees large galaxies anyhow, then that's going to be very difficult to explain with dark matter. That, in my opinion, would be the most interesting discovery the telescope could make. Though I guess oxygen and water on an exoplanet would be a close second. What do you hope Webb will see? Let me know in the comments. This video was sponsored by my friend and colleague, the astrophysicist Brian Keating. Brian has his own YouTube channel, which is called Into the Impossible. He has a lot of interviews with big thinkers, including Nobel Prize winners like Adam Rees and Reinhard Genzel and Roger Penrose. Besides the interviews, Brian also explains some tricky physics, such as birefringence or sterile neutrinos, and he offers his opinions on some of the more speculative ideas that are floating around in physics. For example, the multiverse or conformal cyclic cosmology. I find his channel both educational and entertaining, and it's always worth checking out what he's been up to. If you're interested in what I talk about on my channel, it's very likely you'll find Brian's channel interesting too. Link to his channel is in the info below. Thanks for watching. See you next week.